All right. So chapter 4.1, it begins with by finding the questions become they give you a function, usually powered functions like x squared or something next to the fourth, and they want you to find critical numbers. So critical number is basically whenever a value makes the derivative equal to zero, that's your critical number. And if you remember, um, let me get a graph out. I guess I can just draw you one. So let's call this right here some point A, some x value A and x value B. These happen at peaks and valleys, right? So the critical numbers are values that make the derivative zero. And if you remember, do you remember what kind of slopes are at these locations of the tangent line? Okay, so since they're horizontal lines, right? Those derivatives are zero. The slopes are zero. So using that idea, that means that the derivative is equal to zero of this function at these locations. So if you try to find values, let me find the question here. That make the function zero or the derivative zero, then those could potentially be maximums and minimums. So when you're finding a critical number, they're possibly mins and maxes or local mins, because technically this goes on forever. So there's a maximum here, a local max, and a local minimum, right? Does that make sense? Like where we're going with this, like why we care about critical numbers. All right. So given a function, I'll show the step-by-step process. Now here's a random problem from the homework. I think they give us a picture. Let me see. One moment. Too many damn tabs open. That's what it is. Okay. Now this is number 3 from the homework. There it is. All right. So they want us this before we do. Actually, you know what? Before we get to that, I think this will be better. Sorry about that. Still in spring break mode. Let me wake up a bit. Right. So just find the critical numbers. That's all we're gonna do. We're not gonna talk about maximums just yet. But that's where we're going. Okay, so step 1. Find f prime. Okay. So the derivative will just be a power rule, right? Let me know if you need me to show some steps. I'm assuming you guys are okay with the power rule. Is that all right?
Yeah.
Okay. So let me know. So that's step 1, find that guy. Step 2, set f prime of x equal to 0 and solve for x. These values will be the critical numbers. Okay, so here we go. Setting the derivative equal to 0. Factor 4x squared, right? That's what's in common. That'll leave us x minus 6, right? So set each part to 0 like we always have. So x is 0 and x is 6. So critical numbers are x equal to 0 and 6. There any questions on how to find them?
Oh, that's pretty straightforward.
So those values could be local minimums or maximums. Okay. So eventually we'll be using this idea here. One second. Where is it? Oh, let's go to Desmos. Can you guys see the grapher? Okay. Okay. So the original is x to the fourth minus 8x cubed. Here's our graph. So right there, remember at 0 we have a critical number. So critical numbers could be multiple things. Here, it goes from from increasing to decreasing. This is called the point of inflection, which we'll talk about more later. But it's also a critical number. Over here, it's way down there. Way down here at 6 is our other critical number. It turns out to be a local minimum. So later we'll have tests to figure out what exactly is going on at these critical numbers, but first step is let's find them and move on. Any questions on how to find them? Okay. Excuse me. This allergies are messing me up. All right. Next example. So if the interval is closed for your when they ask about extrema, so here I'm going to ask you find the extrema value of f of x equal to x cubed minus 3/2 x squared. Okay. So there's a theorem in, I think it might be this math book, but basically says the maximum and minimums will happen at critical numbers or at the endpoints of your closed interval. Okay. So since it's closed, we got to check those endpoints as well as the critical numbers. So take your derivative. Let me write the steps first. So step one, right, we got to find the critical numbers. Right? So we said to find this the critical numbers, we have to take the derivative. So first step of step one, get f prime, which will be this. Then set this to 0. set f prime to 0. Solve for x, and we will get this guy, right? We'll call this sub-step, I guess. Okay. Then, of course, solve for x, so set this to 0. One second. Yeah. Yeah, there we go. So these are the critical numbers. Okay. So those are the major first step. Step 2. Writing some notes here. Okay. Test x equal to 0, 1, -1, and 6 by plugging them in. Into f of x. The biggest output will be the max. The smallest or most negative. So when it's closed, you don't have to use any special techniques. You just plug numbers in and figure out, okay, what's bigger. Okay. So here we go. All right, let's start with 0. F of 0 into the original function. That's going to be 0 cubed minus 3 halves times 0, which is 0. So far, that's the smallest. F of 1 will be 1 cubed minus 3 halves times 1, which is -1/2, right? Okay. F of -1, that'll be -1 cubed minus 3 halves times -1. That will be -1 minus 3 halves. -5 halves. So far, this is the smallest. And 0 is the biggest. F of 6 is 6 cubed minus 3 halves times 6 squared. That's 54. So about 162. So what is the minimum? What is the maximum?
-5 halves and 162.
Yeah, so just choose those two. So since it is a closed interval, right? So what I mean, the function is only on this interval. Then you can just do this. Plug in the endpoints of your interval, -1 and 6, and plug in your critical numbers, whatever you find. Those would be your max and mins. And then you can graph it to like check yourself. Excuse me. There. And if they ask for the point, you'll have to plug it in, but I'm just gonna go ahead and give it to you. Save some time. So maximum at 6 comma 1. Well, actually, I already did it. Yeah, what am I talking about? Minimum at -1, 5 halves. Any questions on example 2? Alrighty, move on then. Let's do another one. Find the absolute extrema of f of x equal to 3 cosine x. And it'll be close. We'll do one more of these type, and then we'll move on. Okay. So we'll shorten the steps this time. Step 1, derivative. What is derivative of 3 cosine?
-3 sine x.
Yeah, -3 sine x. All right, second step. Set this guy to 0. So that would happen on the unit circle, right? When x is 0 and x is pi. Yeah. So we have 3 locations to test: the endpoints and this pi. This critical number is the same as the endpoint, so it's just the same point, right? So 3, plug in x equal to 0, pi, 2 pi to test what is the max and min. Okay, so here we go. F of 0 would be 3 cosine 0, which is 3, right? What is cosine of pi? Yeah, it's going to be technically the first one is 3 times 1 and then 3. This will be 3 times -1, which is -3. 2 pi will be 3 cosine of 2 pi equal to 3 times 1, which is 3. So we have 2 peaks, which makes sense, right? Because remember, cosine, it's cyclical. This is going to have a couple of maximums if it keeps going. So at the beginning, it's up at 1, it's at 3, and at the end, it's at 3. So we have 2 maxes, or I should say, maximums. Technically, global max or absolute max. We'll say absolute max at 0, 3, and 2 pi 3. Absolute minimum at pi comma -3. Any questions on example? I think it was 3 actually, no. Yeah. Okay, you guys cool on 3 then, right? All right. Let's look through the homework so you can get an idea. So here, find the value of the derivative. You should see that this is a local minimum, or actually absolute minimum here. So the derivative should be 0 at this location because the tangent line will be 0, right? So the slope of this line is 0. Over here we have 2 peaks and valleys. So they're asking, well, what's the derivative going to be at this location? Well, you should know the slope of the tangent line is 0. Derivatives give you slopes of tangent lines. So at this location, it's 0. This location, it is 0. The slopes are 0. Number 3, this is a cusp. You see how it's kind of jagged at the end or at the bottom? Whenever you have this kind of shape, it's technically not differentiable here. It's not smooth. So the derivative will not exist here. So when you try to plug it in, you find the derivative of this guy, plug it in, you're going to get division by 0. And the graph kind of tells you, hey, yeah, I'm defined here, but the derivative isn't. We have this kind of shape. Any questions on the first 3 so far? Okay. Number 4. Here you can see it's closed. It stops at 1. It starts at 1 and stops at 4. So the peaks and valleys are relative or absolute extrema. Extrema values are just possible max or minimums. So right here, this peak here is a maximum, and so is this one. So at 1 and 3, we have maximum. So I just want you to look at it and understand what are the relative max, absolute max. So those tend to be this. This happens to be the same because it's closed. It doesn't keep going. So if it is truly the highest point, then you say absolute max. If this graph would have kept going, like let's say, oops, where's my pencil? Right, let's say it did something like this, right? Horrible drawing, but since it goes on forever, this would become a relative max. But if since that doesn't exist, these are uh absolute max. Does that make sense? It's also open here and here, so we can't plug them in. But at 2, it's the lowest point. It is defined here, so you would have a relative minimum. And that would be the same because it's the lowest point. So this is a conceptual question. It's a good question. Any questions on 4? Okay. Five, 6. These are the ones that we did together, something similar. So I'm going to move on. These are the closed examples. Okay. And an hour left. Let me see here. Let me check the syllabus real quick. Turn recording back on. So this guy, like why was this pi?
Yes, that one.
Oh, okay. Yeah, it comes from the unit circle. Here, let me show you the graph just to refresh your memory. One sec. Yeah, that's fine, Vanessa. I got you guys. Just as long as y'all do it, that's what matters to me. Just don't get behind too much. 'Cause then things get difficult. Okay, so let's just look at the normal sine. Okay, so sine function looks like this. The period, let me back from pre-cal. This is one period, 0 to 2 pi. So at 0, sine is 0. At pi, sine is 0, right here. So we were looking for when is the derivative equal to 0, but since the derivative turned out to be -3 sine, I knew it was going to be the same values. It's just slightly changed, the -3. -3 just flips it over and makes it a little bigger, but the zeros will be the same. So I knew from the unit circle, this will be what makes the derivative 0, which means they are critical numbers by definition. Does that help?
Yeah, that helps a lot. I was just forgetting that. Thank you.
Yeah, no worries. Okay, let's move on to the next section then. And I'll open up the homeworks in a bit after class, I guess. Okay. Where were we? So 4.2, I'm gonna leave that to you guys. It's like very short, but it's very conceptual. So please watch the videos or read up on it. It's like 3 questions, I think. I want to move on to 4.3. I'm not going to test you on it, but if you choose to do it, I might have some extra credit problems on test 3. So it's up to you. Y'all remember increasing and decreasing from college algebra, like for a function. Oops. And the first derivative test. Okay. So let me give you just a random graph. Just making it up. So let's say we have some, oops, that looks stupid. Let's put up this. Okay. So from left to right, I want you to picture like a little car driving. So the headlights will be pointing upward. So that entire time we consider from left to right an increasing interval, which is also related to your derivative. Remember we said the slopes of the tangent line are positive when the function is increasing. So since it's going to be increasing all the way until the maximum point, which is going to be a 0 derivative, right? Horizontal tangent. From here to here, we're increasing. And then right after, we're going down. So picture your little car, headlights down. And then it gets to, I drew that kind of weird. Obviously, I have no art skills. It's all right. And there we go. Okay. So do y'all see how this is increasing again? Decreasing all the way down here. Zero at the valleys and peaks, right? Then increasing again. So for these first few problems, I want you to be able to identify the intervals where they are increasing and decreasing. So it's kind of stuff you've done in college algebra, but you're going to use calculus to do it instead of, just graphing it. So just pretend you don't have a graphing calculator. Pretend it's the 1800s, right? Okay. So identify the open intervals on which the functions function is increasing or decreasing. So this one's pretty easy. We've all know that this is a parabola, right? Opening upward. And we know that part of the parabola will be decreasing and the other part will be increasing. But let's pretend we didn't know that. Let me see. Let me show you the steps. Step one. Find f prime. F prime will be 2x minus 6. Step two. Find the critical numbers. Remember, set f prime to 0. Here we go. 2x minus 6 equal to 0. 2x equals to 6. X is 3. So we have a critical number at 3. And I'll graph it after this so you can see it better. Anyway, so this is when we use the well, I don't know if we should do that just yet. Um, No, that's fine. We'll go ahead and do everything. Step 3. We'll do it on the next page. But so far, you guys still with me, right? You take your derivative, set the derivative to 0, solve. Here's my critical number. Now we're going to test around the critical number to determine the intervals of increasing and decreasing. All right, we're pretending we don't have graphers and we don't know what it looks like. All right. Step 3. Use the first derivative test to test around. Let me write that better. To test around the critical numbers or number. Okay. To determine if it is a max / min. So this is how you use the first derivative test, okay? So I usually just draw a line like this. Put my critical number in the middle, which we found to be 3. It's my special number. Test any number, remember, before and after critical numbers, or at a critical number, you could have a max or minimum. So if you have a max or minimum, then that means it has to change from increasing to decreasing. If it doesn't, then it is not a max or min. It's probably something else. So I'm going to choose easy numbers. 4, I guess. And find out, is it negative, is a derivative negative here? And is it negative or positive there? Okay. So plug in 0 into the derivative, which will be 2 times 0 minus 6. This is a negative number. So I'm negative right here. So now find out what's going on at 4. The derivative is negative here, which means it has a negative slope. F of 4 is equal to 2 times 4 minus 6, which is 8 minus 6, which is 2. So over here, we're positive. So we're decreasing all the way until we get to this number, critical number, and then we begin to increase. So what shape am I creating? Is this a minimum or maximum?
Minimum.
Yeah, so you can basically infer what the function is doing or what it looks like and find minimum and maximums using the derivatives. So find a critical number, test before and after, and then you know what it is. So if it's plus minus, then it's going up and then down, which would be maximum. If it doesn't change, if they're both minus or both max, or sorry, both pluses, then it's not a min or a max. And that happens. So we have minimum at 3. I don't know what 3 is, or sorry, what the y value is, so you'd have to plug it in. So plug in 3. See what you get. 9 minus 18 minus 16, negative 25, right? Okay. So all this work just to find out if it's a min or a max. But if you graph it, you will know right away, of course. And we know what parabolas look like, so you should be able to figure out where min and max happen, right? We all know that they happen at the vertex. So let's go to the grapher. But before we move on, you guys cool on this idea? Do you understand how to do the first derivative test? I'm going to do a couple of them, but do you see where we're going with this?
Yeah.
Excuse me. What was I going to do? Sorry. I'm getting tired. This is original function was this. Okay. All right. We can see, right? At 3, the critical number that we found, it is indeed a minimum. And we are decreasing all the way until we get there. And then we have a zero derivative that increases all the way. So without the graph, can you determine what the interval is for decreasing? That was the original question. I just did the minimum for the hell of it. Well, it kind of helps, but right, we're decreasing from negative infinity all the way until 3. And then right after 3, we're increasing, right? And we continue to increase after 3. Does that make sense? We can see it here, right? Negative infinity till 3, decrease. 3 to infinity, increase. So all you need to do is test one point after your critical number with the derivative, and then you can determine that it will continue to increase the entire time. And the reason we can do that is by looking at the definitions. So we won't have a change in it won't go from increasing to decreasing unless you have a critical number. Okay. So if it changes, you have a max or min, but that'll only happen at critical numbers. So just write the intervals before and after using your derivative to infer. You guys have any questions on this first example? We did a very simple one, a very simple function just so you can get the main idea. Obviously, this is unnecessary, right? Okay. Any questions on finding those intervals or the max or minimum? I'm going to move on to another one. Okay, let me pick another question. All right, one sec. Let's do number 8. It's a little more complicated, I guess. This time I'm gonna graph it first. Let me write the question down. Okay. Mhm. Let me make this look a little prettier. There we go. So this is the function we're going to work on. Again, we're not using a grapher or solvers or anything. The whole point is to use derivatives to figure out this maximum and minimum point. Okay. So we should have two critical numbers when we get to that point, and we got to test when we test around it in a moment. We should see that it's increasing before this critical number and then decreasing right after. Over here, we have decreasing and then increasing. So we should have a max and min, local max and local minimums happening. So that's where we're going. But we're doing it the hard way. Okay. Find the local max slash min, also known as relative max and min. Find the intervals for increasing slash decreasing. Probably in B, I guess. Step 1, find critical numbers. So first step, find the derivative. That will be 6x squared plus 12x minus 48. Set this to 0. Okay, this factors, I think it factors pretty, right? X plus 4, x minus 2. Which we already knew these numbers based off the graph, right? Any questions on step 1 here?
Wouldn't the minus 48 become 0 when we took the derivative?
It was a 48x.
Oh, I did not see that. My bad.
No, thanks for checking. Okay. Step 2. We're going to test around these 2 points, okay? Test around x equals -4 and x equals 2. And so here's my little line, -4 and 2. Okay, let's pick some easy stuff. I will pick 0, 3, -5, I guess. Plug these into your derivative, see what's going on. So -5, that will be remember, all we care about is it positive? Do you believe that this is positive? And if not, add it up. What do y'all think? I don't know what that is. Let me see. Looks positive to me, right? Thanks. Space. Let's try the easy one. 0. The minus here. So that means we're going up, then down. Right? So maximum most likely here. All right. 3. What is that gonna be? 6 times 9 plus 36. Positive for sure. Okay. All right, so excuse me. What is it gonna do? Oh yeah. Yeah, it's true. That's kind of weirding me out. This is making me doubt this one. Oh well, that's fine. All right. All that matters is it positive or negative. So where is my maximum? Where is my minimum? So we went from plus to minus, so we have a maximum at -4, comma something, right? Minimum is gonna be what? Right? Minus plus 2, comma something. Don't feel like plugging that in. Desmos said that this is 160 and this is -56. So I'm going to skip a minor step because I believe you can all plug numbers in. Y'all are sharp. Okay, so where are we increasing?
As we approach the -4.
Yeah, everything before -4, right? All is increasing technically. Increasing. So we'll have a negative infinity all the way until -4. Then we start increasing again somewhere else, right? Y'all see over here after 2. So these are the two intervals, do a union symbol, where we are increasing. Where are we decreasing? I know my drawing sucks, but I just
-4 to negative, till 2.
yeah, just that middle part, right? And that's it. Just that one little section. We're increasing before -4 and increasing after 2, but only decreasing in the middle. Let's look at the graph again. Did we mess anything up? So increasing, right? All the way up until -4. Decreasing in the middle section. And then increasing after that. So yeah, looks legit. So do you see how we can use the first derivative test to find the local max and mins, or relative max and mins? And then with that information, you can kind of figure out where you're increasing and decreasing. Does this make sense?
Yes. I just have a question.
Sure, what's up?
Does it matter what test numbers we use?
It does not. Use numbers before and after a critical number. You choose whatever is easier, is what I recommend.
Okay.
Guys have any other questions? Okay. I'm going to reopen the last few homeworks for chapter 3. And I'll let y'all work Thursday. Let me take roll and we'll call it a night. Balkis Askar, Jordan Sanchez,
Here.
Alexandra Luna, Asia Carrillo,
Here.
Armando Rojas, Haley Gibson, Chance Kleins,
Yes, sir.
Gavin Montemayor,
Here.
Matthew Packard,
Here.
Jose Perales, Christina Sayundo,
Here.
Michelle Berlanga,
Here.
Vanessa Ventura,
Here.
Zachary Villarreal,
Here.
Jeremiah Williams.
Here.
All right, guys. Well, see y'all next time. I'll post this as soon as I can, okay?